My name is Lakesh Sharma. I'm a soil and water sciences uh, soil fertility specialist. I'm a BMP coordinator, and I'm the organizer of this BMP summit, along with Dr. Michael Dukes, Director, Center for Land Use Efficiency. Today's session, we have three speakers. Dr. Mark Clark, Associate Professor, Wetland and Water Quality Extension Specialist in Soil and Water Sciences, and Bob Hockmuth and Jay Capasso from Swanee Valley. And Bob and Jay will be the second speaker for this session, and Mark will be the first speaker. Mark will be presenting on legacy phosphorus. So Mark, the floor is yours.
Great. All right. Thank you very much, Lakesh. Good afternoon, everybody. Hopefully I can keep you awake after your lunchtime extravaganza, whatever you may have had. But this talk's going to be about legacy phosphorus. I suspect many of you have maybe heard the term before, but hopefully this will give a little bit of context around where the terminology came from, what the implications of legacy phosphorus is in the landscape, and what some efforts are to try to address it. So here's just some imagery down at the bottom of this slide that shows how our technologies and application of phosphorus in that landscape have changed pretty dramatically. Just a very broad, crude kind of application, not, I'm sure, very even, to something that was more of a uniform spreading, to now drop spreaders wherever it is appropriate to apply based on things like soil tests. But this legacy phosphorus you'll see is a result of these historic sort of applications that may not have been refined as they are now. And as a result, we are now having to address those historic, let's just say, inefficiencies in application. All right, so just a quick overview of where we're going with the presentation. The first part will be talking about what exactly is legacy phosphorus and how does it actually develop. Some implications for natural systems, implications for the regulatory environment under which the terminology was to some extent established, but how it's kind of driving much of these TMDL watersheds we live in, certain mitigation mechanisms to try to address it. And then I'm going to give you a brief case study about the Northern Everglades. It probably has the most significant legacy load that we know about, but the implications are pretty large. So provide just a couple of slides there to wrap up the presentation. All right, so what exactly is legacy phosphorus? So it's kind of, legacy is relative to contemporary. So part of this is about historic applications of phosphorus relative to today's or maybe this year or even recent applications. So it's a relative context within time as to when the phosphorus applies. But it's not just fertilizer phosphorus, it could be other sources that have been applied. Biosolids, might be even natural sources that have been exposed due to disturbances of some sort, either say excavation of a channel through a phosphatic rich layer, or in urban landscapes where we're using fill material that is actually coming from phosphatic sources. These could also kind of fall into this legacy phosphorus, but it's basically these historic applications, not the new or the contemporary applications of phosphorus. And the term was really coined as we tried to develop watershed phosphorus budgets and trying to understand what could be addressed through management practices of new applications of phosphorus versus what might have to be addressed or to kind of partition out this historic load that really an owner of a property or somebody that's trying to manage a crop has limited control over. They can recognize it's there. They can modify some practices in response to it, but really can't do much about it. And you'll see that present BMPs only have a minimum focus on these legacy loads. It's more about the contemporary application. So the slide on the right is just to recognize that even though phosphorus is quite common in Florida, that's not what we mean by legacy load. We're really talking about the application of phosphorus through fertilizers or other sources in the past that now essentially we're having to address because they are contributing to runoff components. All right, so to put this in a little bit of context or understanding, we got to talk a little bit about phosphorus chemistry. We're not going to go too much into this, but kind of need to realize how phosphorus behaves in the landscape. So if you look at the diagram at the bottom here and assume this is a agricultural field. Let's just start with a natural background ecosystem that perhaps has weathered over long periods of time. And really the only directly available pool of phosphorus for plant uptake or biological uptake is this soil solution P. So this is where our phosphate might be. It would typically be associated with the pore water. So this phosphate's dissolved in the pore water, and then if a plant was to take up that phosphorus or a microbe was to interact with that phosphorus, it basically is the directly available form of phosphorus. And so this is the smallest pool typically in the soil, is this solution P pool, because it's constantly being mined by vegetation, but it's also interacting with other components of the soil, other chemicals and elements in the soil. It can be absorbed by things like iron and aluminum if you're in a more acidic soil, or by calcium if you're in a more basic soil. And that absorption would be removing that solution P phosphorus. You can also get precipitation in the formation of secondary minerals associated with the P in that P solution can basically precipitate out and form minor minerals. We can also have some parent material or some more recalcitrant type of minerals that can form as what we call primary minerals. But all of these sinks, or basically removal of soil solution P, can also be broken down either through weathering or dissolution of a precipitate or desorption of a sorbed compound. And so what we actually have here is phosphate moving back and forth between these pools. So smallest pool here in the middle that's accessible to biological uptake, but there's this competition with these pools that are not really recalcitrant, meaning they can be mobilized. So these are actually bioavailable, not directly, but they will be released when the solution P goes down. So these are what we've referred to as in equilibrium. So there's movement back and forth. This soil solution P, once immobilized in the living plant or the living organism, is essentially also immobilized or not available for additional uptake. But that biomass or that living matter, once dead, can essentially release that phosphorus back into the solution. So this solution P is really what is the directly available, but it's in competition with all these other kind of pools. Now, if we want to enhance this solution P to facilitate increased availability and therefore maybe crop production if we have some limitation, we need to add phosphorus in the form of either an inorganic fertilizer or maybe some sort of animal or plant residue to boost this soil solution P. But remember, the second this goes up, it's also interacting with these other pools. And so as we try to achieve a higher solution pool P to assist our plant growth, we're also basically, feeding is the wrong word, but increasing the storages in these kind of short to longer term storage potential. So we're not just adding P to this soil solution area with our fertilizer application. We're also essentially accumulating phosphorus now into these soil components, okay? Now, another big thing about the phosphorus cycle, which would be very different if we were talking about the nitrogen and the carbon cycle, is that phosphorus has no significant gaseous phase, meaning we don't have phosphorus floating around in the atmosphere unless it might be a particle or something like that. There is something called phosphine gas, and we need to be very thankful that we don't have that. It's highly toxic, but fundamentally, without an atmospheric component of phosphorus, once phosphorus is added to the soil, for the most part, it never goes away. It may move downstream, but fundamentally, once it's in the system, it essentially is just moving between these pools, may run off and then move between pools in an aquatic system, no pun intended. But either way, you have this situation with phosphorus where once added, essentially it's a shell game and it just moves around either in the soil or downstream into varying degrees of recalcitrant availability. Now, if we just simplify that previous diagram to this diagram, what we see is the solution P, it's interacting with this active phosphorus pool, which means these are exchanging back and forth. And then some of that active pool can also be fixed into a more stable pool, but it too can be released and come back down through the system. And so as we try to increase this pool to improve our plant or minimize our plant limitation, we're also building these other pools up. And so that's really important that we're not just influencing this solution P pool with a fertilizer application. We're really influencing all of these others. And that can be beneficial because now we have kind of a slow release component or slower release component here than just an immediate response, and that these are in equilibrium. So as we load up this solution P pool, it kind of pushes phosphorus towards this absorption sites. And then as we deplete the solution P pool, things start to come off these absorption sites and desorb, or basically mineralize or dissolve back into solution. And so this is an equilibrium that goes on in that soil chemistry. To visualize this a little bit more, and this is really what we do a lot of times with lake sediments, but either if you had a flooded soil or you had sediments from a lake, and you took a sample, and so that's what these two containers are on the right. And the first container, you flooded that soil with a solution of, basically let's call it water, with no phosphorus in it. Okay, so this is a low phosphorus or no phosphorus water flooding this soil. And then in our other container, we had the same type of soil, same site or whatever, same chemistry, but now we flooded that with a high phosphorus concentration. What we would see over time if we started to measure the phosphorus levels in the water column, and remember this bottom one started with no phosphorus, the top one started with some phosphorus. Over time, what we would see is the concentration of the phosphorus in the water that started with nothing would rise, meaning phosphorus would be released from the soil, or in this case, the phosphorus that was bound to the soil particles and released into the water column. And what we would see in the sample up top here, where we flooded with high concentration of P, meaning we just fertilized it, perhaps, or we had flood water that came down and entered into a lake that didn't have elevated phosphorus before. What we see is in that instance, we have phosphorus moving from the water column down into the soil. And this is something we call this equilibrium phosphorus concentration. But really what this is illustrating is the fact of this movement back and forth between the phosphorus that's in solution, the phosphate in solution, and these particles or the soils that could be sorbing and desorbing constantly. And so that equilibrium is driven by the concentration. If you fertilize, you drive phosphorus basically into some of these soil pools. If you deplete that solution P to as much as the soils can make up for that, they will basically release that back into solution. So this can happen at the interface of a lake bottom, or it could happen basically in the pore water or at the pore water scale in your a soil sample. Okay. So how do we go about measuring the amount of phosphorus that might actually be on the soil or in the soil or available, or as we start thinking about legacy P, accumulated in the soil beyond some point at which it might be desirable? And so as we apply phosphorus to a crop, some of that phosphorus is actively taken up by the plant, but a large percentage of it is actually not transferred or efficiently taken up by the plant, and instead it's left in the soil. And some of that is maybe tightly bound, but a lot of it is in those fractions that are semi-loosely bound. And the soil test P, when you take it, and there's lots of different types of soil test P's, they're all measuring kind of different components, But what it's doing is it's estimating the remaining bioavailable pool. It does not extract the really recalcitrant, or what we refer to as the residual pool, the fraction that's there that cannot really be mobilized by the plant. So the total phosphorus in the soil and the extractable or the bioavailable are not the same number. Total phosphorus is always greater than the bioavailable fraction. And the more, primary minerals or residual or recalcitrant sort of organic compounds, the less available some of that P may be. But a lot of that P can be in a form that the plant can extract, quote unquote, mobilize around their rhizosphere because they have a slight acidification process, and then be available and take up. And so, as you all know, through your soil testing, you'll get a result from the analytical lab you sent it to, and it'll give you an estimate of the available phosphorus that's there. Now, when you have an acidic soil, the fraction of that soil P that's kind of temporarily bound is in the form usually bound to iron and aluminum. There's lots of other different compounds in there, but if it was a more basic soil, it's going to be bound to calcium. And so the iron and aluminum bound or the calcium bound P are the pools that kind of are in this equilibrium with the solution P. And the rates of exchange are one thing that we might have some questions about later on, and I'm not going to go into it here, but I think that's one of the challenging aspects of the soil P test extraction, which measures a kind of a potential available, but the rate at which that availability occurs is going to be different. And so the plant demand rate and the actual soil supply rate may not be characterized accurately or adequately with a soil test. All right, so because we know that iron and aluminum are primarily elements in the soil that the phosphorus is interacting with, we can actually make an estimate of the amount of storage capacity, meaning kind of the retention capacity, but still in equilibrium, but a retention capacity of a particular soil and how much phosphorus can it retain. And so the equation up here in the top is something called the soil phosphorus storage capacity. But what it's doing is it's looking at the ratio of iron and aluminum to the amount of phosphorus in the soil. So if we have iron and aluminum present, we know we can bind up some phosphorus in that soil. The more iron and aluminum we have present, the more phosphorus we could bind up. As we add phosphorus to the soil without adding something like iron and aluminum, over time we'll start to satiate, or mean we'll have excess phosphorus relative to the binding sites of iron and aluminum. And so by measuring not just the phosphorus in the soil, but the phosphorus, the iron, and the aluminum in the soil, we can start to develop a estimate of how much absorption capacity or excess phosphorus we might have in the soil. And so the graphic here represents a range of soils that were collected in different locations, and this equation essentially was developed for them. So this soil phosphorus storage capacity was applied, and any value that comes up positive means it has excess iron and aluminum relative to phosphorus. So we have more binding sites than we actually have phosphorus. Any negative number means we actually have excess phosphorus relative to the amount of iron and aluminum that are present. And what we see then is that our points are distributed both in positive and negative areas. But the second we move into a negative SPSC, we see the water-soluble phosphorus increase, meaning when we have positive values, we have adequate iron and aluminum in the soil to lock up the phosphorus essentially. Some of that is still plant available, but a lot of it can start to become less available. But once we move into this negative zone, we see the water-soluble P starting to increase, and it's proportional to the degree at which we don't have iron and aluminum to bind up the phosphorus. And so if we were to continually add phosphorus to a soil, and there's a finite amount of iron and aluminum, we are starting to accumulate P in excess of its absorptive capacity, the soil absorptive capacity. And what we start to then see is the increased likelihood of leaching, not just vertically, but essentially also historically, horizontally, and the increased potential for runoff downhill or downstream. So what are the implications then with regards to this phosphorus accumulation in the soil in response to excess? And excess means that fraction which is not actively taken up by the plants and it is now accumulating and essentially building up this reserve. And if we do that, look at this at the watershed scale, what we see is that initially that background condition, and so the red line is the soil P concentration, and this would be, you could just have it as Mehlich extractable, or you could arguably say this is even total, but basically the red line prior to, let's say 5,000 years ago, this is where we were with our red line. We had phosphorus that probably was weathered away out of the soil, especially in Florida with high rainfall and sandy soils, not much to hold on to it. But as we started to fertilize that landscape in the effort to improve yields, we started to indeed improve yields, but we also started to accumulate phosphorus in those soils. And so as we were accumulating phosphorus, we started also to see increased runoff. And so the graphic in the bottom here is the phosphorus runoff response, theoretical, relative to this P accumulation in the soil, and of course the additions of phosphorus. And so over time, we're improving our yield because we're applying fertilizers. That fertilizer is not just producing new biomass, but also accumulating in the soil. But during that time, we're also recognizing increased runoff in the watershed. It's starting to affect the downstream ecosystems. That increased nutrient availability can increase primary productivity, eutrophication. We can impact our water resources. We can now have something called an impaired water body, which trips things like TMDLs, BMAPs, BMPs, all the things we're starting to enjoy in many landscapes. But what those TMDLs, BMAPs, and BMPs do is all of a sudden focus on this fertilizer application rate. And it's not that we don't have soil tests that have been around for a long time, but all of a sudden it becomes dramatically poignant to try to do something. And so we make our best effort to now cut off or minimize any new inputs. But that's when things don't automatically drop to zero in the sense of the runoff. Now what we have is this accumulated phosphorus in our soil that will still be releasing phosphorus both to our plants to some extent, maybe not to the maximum extent of yield, but still providing some bioavailable phosphorus, but it's also still releasing into the environment. And I have this little wedge out here because as the soil phosphorus starts to become depleted, one would need to re-engage some sort of fertilizer application rate to make up for whatever that available pool is. And one challenge right now is whether or not this wedge needs to come all the way over to this point at which we think there's adequate soil P, but there still may not be to maximize yields. And so what we have here is, even though we may be implementing TMDLs, BMAPs, and BMPs, is that the only way to get rid of that is to fundamentally send it downstream. And because we're not locking it up in the soil, it's essentially still leaching out in our effort to reduce this up in the upper part of the watershed. And that takes time. So even though we want to implement the BMPs and have a rapid improvement in the system, we have this legacy phosphorus that essentially releases over very long time periods and at a relatively slow rate. And this is this lag time. And so even though we may have the right numbers to implement a return of a impaired water body, the time lag that it takes to actually get there may be quite long, and a lot longer than most of us would desire. So of course, because we have this legacy load, because we've already tripped some sort of threshold of impairment and therefore entered into a TMDL, the implications downstream are already significant. And in Florida and many other areas, this is fundamentally challenging with regards to phosphorus, because phosphorus is oftentimes the limiting nutrient in the natural ecosystem. In agricultural systems, we try to minimize any sort of limiting factor. Sun is about the only thing you can't really do much about. but everything else we try to minimize. But in natural systems, the big controlling variable is oftentimes phosphorus, and terrestrial systems also nitrogen, but especially in freshwater systems. And so our ecosystems are very sensitive to phosphorus. So any additions of phosphorus to that landscape, the natural landscape, are oftentimes resulting in eutrophication or a biological response that sometimes is undesirable. And that even though we can address contemporary loads, the new inputs, this legacy load will persist. And because we've already released those into these biological systems that perhaps assimilated that phosphorus for some period of time, that phosphorus that's now in the natural system accumulates in its sediment, and it can increase its internal cycling. And so even if we were optimally to shut everything off from the watershed, we still now may have a aquatic ecosystem that's been loaded up, just like we loaded up the terrestrial ecosystem, and it now has developed its own internal cycling and legacy load. So what are the implications when it comes to the regulatory environment? Well, first off, as we trip impaired water and trigger a TMDL, there's the first part of it. But the second part of it is, how do we now try to mitigate for that impaired water? And you all are aware of the notices of intent and best management practices that are essentially the approach most, I believe all, agricultural interests implement to achieve a presumption of compliance within a TMDL watershed. You can monitor, but I don't know anybody that's gone down that road. But most of the BMPs in the notice of intent really focus on the contemporary, the modern inputs of phosphorus, not these legacy loads. And for the primary focus is really in the soil test P. Soil test P is designed to determine whether or not there is adequate phosphorus that is residual, i.e. legacy phosphorus that's in the soils that should be sufficient to meet the crop's demand. And I know that there's lots of discussion about whether or not those soil tests are accurately achieving that, but fundamentally that's the objective. Most other BMPs are not really focused on that legacy load. However, certain practices that reduce particulate transport, where that phosphorus historically could have been bound, and if the particle's not moving, then the phosphorus is not moving, and anything that's reducing the volume losses or transport off farm, either through enhanced irrigation practices or just retaining water on site, is basically going to also reduce the vector that otherwise is the phosphorus movement. But most of these reductions in the legacy load are not through the BMPs, but instead are through regional treatment practices and also the cost sharing of usually what we refer to as enhanced BMPs, or these technically possible but too costly practices that a grower can't really carry on their own. And so just as a quick example of what that might look like in a TMDL watershed, this just happens to be for the Lower St. Johns, the freshwater portion of the Lower St. Johns, and this is the agricultural allocation. And we don't really care about total nitrogen here. So what we've got is total phosphorus. And so what we had at the time of the TMDL was an actual loading of about 183,000 pounds per year of phosphorus. The TMDL target identified that 156,000 pounds could still be added to the natural ecosystem and be assimilated without undesirable impacts or impairment. But what that meant was 27,458 pounds of phosphorus had to be reduced from the loading at the time. And of that 27,000 pounds of phosphorus, only, still a lot, but only 20,196 pounds could be achieved, the reduction could be achieved through BMPs alone. Okay, and so that's where you're focused on the contemporary inputs, but what we have is this residual fraction of phosphorus that still needs to be reduced according to the TMDLs, but really can't be achieved through BMPs. And we have, in this case, about 7,000 pounds per year of phosphorus that would have to be reduced through other means than the BMPs alone. And this is kind of where our legacy load turns up. And it's not explicitly that, because really parsing that out is kind of a residual value versus an actually carved out of the landscape or carved out of the budget legacy load. But that's kind of where it falls. And that remaining component is where we now have to look to other practices. And those practices are usually outside the grower's cost. It still may be occurring on their the areas they're actively farming, but from a cost standpoint, it's essentially they are no longer kind of obligated to that. This is a historic load or it's a load that's outside their control. And so this is where we look to these cost share programs and regional type treatment systems to deal with that. And so just as a quick example, this Tri-County Agricultural Water Management Partnership is one way that is being addressed over in the Tri-County Ag area, where cost sharing of alternative irrigation practices, overhead, tailwater ponds, these are things that we know can reduce phosphorus loads and shave off kind of that historic component. But where the biggest input is coming from are these regional treatment systems, where in this left-hand image, which is in the Tri-County Ag area, we see ag fields where BMPs and some load reduction is occurring, but that water is still now traveling to a channelized area and to a tributary, and that would not have been sufficient alone to remove the phosphorus. So this regional system, which has a equilibration pond for hydrologic equilibration, and then a treatment wetland over here for phosphorus removal, as well as nitrogen, is added in. So now water that comes down this channel gets routed through that system, basically, and this system is not the responsibility of the growers. In fact, this is overseen by the Water Management District in conjunction with the county, actually. The bigger systems, I'm sure you all are aware of them, are down in the Everglades area. These are the Everglades stormwater treatment areas. There's about 60,000 acres of treatment wetlands that have been installed between the Everglades agricultural area, Lake Okeechobee, northern part of the lake, and the water conservation areas in what's called the Everglades protection area, to try to mitigate for those phosphorus loads that otherwise would be having negative impacts downstream. All right, so just a quick case study in the couple minutes I have left here. This is about that area down in South Florida, north of Lake Okeechobee. The image here on the right kind of gives you an idea of where that footprint is. It covers about 2.65 million acres. And it is estimated that 80% of the existing loads to Lake Okeechobee are the result of historic, meaning legacy phosphorus loads. This is a pretty active landscape with a lot of pasture, a lot of natural areas and whatnot, especially down here closer to the lake. But the active loading in that landscape of fertilizer P or biosolids P, much of that has been essentially cut off and reduced down to like 20% of whatever the historic load was. But fundamentally, the majority of the load at present is coming from these legacy loads that were applied to this landscape in the past. And despite all of the efforts, and there are many projects and land acquisitions and movement or displacement, let's call it, of dairies that used to be heavily throughout this area, which are now, many of them moved up to the North Florida area. Despite all of those efforts, this is the loading. The graph here on the bottom is the loading as well as the inflow. So the loading is in green of phosphorus to Lake Okeechobee. TMDL line is this dashed line where it was actively implemented, but there was other efforts prior to this that were being conducted. But you can see that the concentrations are still averaging about 500 metric tons per year. The TMDL target is this orange line or yellow line, which is 140 metric tons, of which 35 metric tons is atmospheric deposition. So technically there's only 105 metric tons of phosphorus allowed, if you want to call it that, under the TMDL to be entering Lake Okeechobee from the watershed. And the big challenge, or the big reality, is that all of these projects, they too are addressing the legacy load as well as the new kind of contemporary load, but that the scale of this legacy load is just so large that it's going to take more fundamentally. And to get a time frame on this to some extent is, if you look at this load. And there was an analysis conducted, must have been back in the early 2000s, where it's estimated that the Lake Okeechobee Basin has about 170 metric tons of phosphorus in it. And if we assume that 35% of that is not available and is never essentially going to be mobilized, 65% of that could be mobilized, but of that 65, let's say only 10% is going to be actively mobilized. So we're down to a small fraction of this total legacy load. But even with that being released at the rate of the present 500 metric tons per year, it would take 22 years to clean that system, in the sense of reduce this legacy load back to some historic levels. And if you took only 25% of that total amount that's in the basin and released it at 500 metric tons, it would be 55 years. But 500 metric tons is still four times almost higher than the TMDL load. If you actually released at the TMDL load, it would be on the order of 105 to 262 years. So we're talking about a really long time to bring this system back into some sort of background and get rid of that legacy load of phosphorus. And fundamentally, where are we moving it? We're just moving it out of the watershed and now into the lake. We haven't gotten rid of it. We're just displacing it somewhere else. Again, nothing goes to the atmosphere. It's just a big shell game that we're pushing it around the landscape. So I'm running short on time. So just really quick, there was a study recently done in 2019 that looked at various different approaches, BMPs, as well as these enhanced BMPs and regional storage systems. But fundamentally, what it came down to is BMPs and other kind of enhanced practices would only get you to about a 40% reduction max, unless you added stormwater treatment areas. And you would have to add over or about 200 kilometers square of STAs to achieve the load reduction you need to address the legacy load in the Okeechobee Basin north of the lake. And that would equate to roughly the same area of STAs that are south of the lake, which is essentially 60,000 acres. Meanwhile, as we're debating the whole thing, what's happening? The load or the inflow concentrations in the lake are going down slightly, but the concentrations of phosphorus in the lake are increasing. So again, we're just moving the phosphorus into the lake. We have now internal cycling in the lake, and essentially we haven't really made a whole lot of progress towards the lake's objectives of trying to reduce its load. All right, so I know Lakesh is looking at me like, come on, get it together. So this just in summary, I think what I'll do is I'll let you all read through this, so because I definitely don't want to overstep my time, and address any questions. So feel free to read through this as I respond to any questions that folks may have.
Thank you. Thank you, Mark. So audience, please, you can ask your question in the chat box, and I will ask that question to Mark. I have a question, Mark.
Sure.
For the nitrogen that I know of, that in fully saturated soils, if you apply any fertilizer, I'm talking about a conventional fertilizer, which is urea or ammonium sulfate, usually take between 5 to 6 days to convert all that into nitrate. And is there any study that has give us some information how much time it takes for the fertilizer to get fixed in acidic or basic soils by the calcium or aluminum iron? Is there
I'm sure there are studies. I don't know of them specifically. I'm sure it's there's temperature dependencies to some extent, but a lot of that is not biologically required, so it's direct absorption. I would think that it's relatively quick, but again, I don't know exactly those time frames, and it's going to depend on the form. It would need to be in that phosphate form to be reacting, but I'm guessing it's pretty quick. But I think that's not an area of expertise that I have dug into. But I really think that's a component, maybe not so much on the uptake side, but more or equally important on the release side. Again, the idea that when we do a soil extraction, that's kind of almost an instantaneous measure, but is it at the rate in reality, in the real world, is it at the rate that the plant actually is needing it? And so I think that there's a rate question in here that may or may not explain some of the discrepancies in what we see of the soil test availability and plant limitations still, or plant response to phosphorus. Yeah.
All right, we have some questions. All right, let me go. Okay, Mark, where is the research on removing phosphorus from large water bodies?
There's a lot of it. It's the large water bodies becomes challenging. I think the largest water body, if you want to call the Everglades a water body, is really trying to stop it from going in. Once it's in, it's very difficult to remove it. The Lake Apopka is probably the most effective one, where they found ways to remove it from the water body, because the lake is so eutrophic. It's got a high percentage of its phosphorus and particulate phosphorus in the water column. They take that water, they pump it through wetlands, the particulates settle in the wetlands, and then the water that returns to the lake is essentially lower in phosphorus. So they're extracting the phosphorus out of the lake. But generally, all the efforts to reduce loads once they get into an aquatic system essentially is to try to keep it out, because once it's in, it's really hard to remove because it's in the sediment. They have contemplated dredging Lake Okeechobee at the tune of like $2 billion, but have never found a place to put all the soil. So it's not even feasible in that sense. So it's really more about trying to keep it out than to try to take it out once it's in.
Thank you, Mark. Our next question is, how can a crop producers make their top profit if they are held to BMPs that suggest they don't need or only need to apply minimum level of phosphorus?
Yeah, it's a great question. And I think that's the real challenge. And I believe that if it can be determined that indeed a higher application rate of phosphorus is required to maximize yield, then what has to happen is you have to trap it at the edge of the field, because the added inputs are going to inherently result in increased runoff. And I'm saying that in general terms. I mean, there's obviously some nuances in there, but as a result, you just need to have ways to trap it and intercept that runoff at the edge of the field. Because even though it may increase yield, the efficiencies, as you kind of hone in on that incremental increase in yield, is also going to translate to likely increased runoff. And so we have to have a better trap at the edge of the field if we're going to, continue to apply internally to the field. But I'm hoping we can understand why, even when soil test peak concentrations are 500 milligrams per kilogram in the field, we still get a response to phosphorus. It's illogical, but I think that's where that rate question comes in. If we can understand that better, then maybe we can not have to apply and still maintain the yield. But somehow you're going to have to trap it. If you're going to apply more, we're going to have to find a way to trap it from going downstream at somebody's cost. That becomes the next question: who pays?
Thank you, Mark. Our next question is it common for agricultural soils to be overcharged with phosphorus?
Yes, any that have received historic phosphorus fertilization applications, yes. Generally, they are in excess of whatever a natural background level would be. Yeah.
The next question is, what study was that 80% figure from, that 80% of phosphorus loading to Lake Okeechobee is from legacy phosphorus?
Ooh, so Water Management District. It was part of their TMDL assessment. I would have to go, I got it off their website. I would have to go find it if somebody wants to send me an email, or I can send it to Lakesh and he can send it back to you, or somehow if we can make a connection, I'll get you that document.
Okay, I will take one more question and then we will go with our next speaker. And Mark, you are hanging at the end of the this session, right? Then I will. We have plenty of questions for you, and you can read those questions in the chat box by that time. And I will ask you to answer those questions at the end of the session.
Sure.
All right, so the last question that I'm going to ask is from Melissa. I'm not an expert on this topic, and please forgive me if you have already mentioned this in your talk, but is there a way to make the phosphorus that is already in the soil more available to the plants for uptake so that you would not have to add more phosphorus to the system?
Yeah, it's an excellent question. And I think that, you know, those are some of the innovative ways we may find to utilize this accumulation of phosphorus in a productive way, instead of right now, what we're having to do is essentially mitigate for it in an unproductive way, unless you're into building treatment wetlands like I am. But so pH would be a critical one. If, you know, if the soil pH is not optimal, then it may be that some of that phosphorus could be available if it was essentially improved upon. There are other methods underway to try to increase that availability, but I think that that comes with a little bit of a tentative approach, because one concern would be is by increasing the mobility, if the plant doesn't take it up, then you're also increasing the potential mobility offsite. And so it's a fine line in there as to whether or not you can really target the plant's ability to access it versus actually exacerbate the problem by now releasing it into the environment. But excellent question. I think that's an area that really needs some investigation. So.
Thank you, Mark. You can read the questions, and we'll get back to you at the end of the session around 2:20 to 2:25. All right, okay, you stop the share screen. Okay, Bob. We have our two speakers, Bob Hockamuth and Jay Capasso. Bob is a Center Director for North Florida Research and Education Center, Swanee Valley, and Regional Specialized Agent. Bob has worked a lot recently on control release, I would call smart fertilizers. That's a very fancy term used for these fertilizers. And Jay Capasso, who has worked in with the same fertilizer in corn, and I think Bob has worked in carrot and corn and some other crops. Okay, Bob, the 40 is yours, and here we go.
All right, everything's good with this, with the screen sharing.
Perfect.
Okay.
Actually, Bob, can you go up to display settings and click swap? Yes.
Yep.
Okay.
Perfect. Thank you.
All right. You're welcome. Okay. Jay and I are looking forward to kind of giving an update on some of the controlled release fertilizer work that that's going on up in this North Florida region. It's sort of an update from a presentation at last year's summit, where we kind of went over the introductory part of this particular topic. Just for those of you that are not in this particular area, we want to make sure that you're aware we've got a big challenge ahead of us, sort of similar to the things that Mark was touching base on in other parts of the state. Here, our challenge is in fact nitrogen, and this region as a whole, we've got to reduce the nitrogen load by over 4 million pounds to meet the BMAP in this particular area. And this map on the right-hand side sort of gives you an idea of the cropping area. This is a very rural agricultural area throughout this this whole region, with a lot of pivot irrigation systems and drip irrigation systems for crops that are appropriate for those two means. So this is the region that we are working in. Deep sandy soils, and very high likelihood that nitrogen can get away from us in these soils. So just a bit of an overview. Like, first, I want to make sure that we sort of don't call these slow release fertilizers, because the release is actually based on the technology, and some release rates are slower than others, of course, but to use the term slow probably is an old term that doesn't necessarily fit the current technology today. Currently, the polymer or resin coatings are what is being researched and looked at for these large open agricultural areas. And I think traditionally, if you look at some of the ornamental horticulture area where controlled release fertilizers have been used, that this is a whole new deal in moving into open field agriculture. The interesting thing here is that the main release curve in these materials is based on temperature, not moisture. So what happens inside that polymer, once there's adequate moisture inside the polymer, the actual release rate is more based on temperature than it is on moisture. So this is the area, this improved timing of that release curve is what really has changed things from an unpredictable fertilizer program to today, where we have a lot better handle on what these release rates and utilization by the crop should be. And an individual fertilizer material that would be used for potatoes or watermelons or corn would be built differently based on the release curve of that particular crop, and also the temperatures during the season in which those crops would be grown. The thing that makes it a little bit difficult for these controlled release materials is that if the season is very short, say a 60-day crop, it's really hard to build a polymer that is going to be able to release early enough in that crop. So it actually is a little easier to build a release program for something like watermelons or corn that are much longer in the season. But crops like snap beans and some of the short season leafy greens are a little bit more difficult to build that polymer because you can only go so thin with that polymer when you need it to release quickly. So you're almost headed towards conventional fertilizer without any polymer coating at all when you get to these real short season ones. So just to point out that the seasonality, the length of the season does dictate the difficulty in putting together these polymer coated materials. They are expensive. It's a high quality material. I do look at it as an advanced technology in the fertilizer world, and certainly fits our advanced BMP program. What we are seeing, and I think as we go through this program, that you'll hopefully see where these materials, it looks to me like, could play a very important role in helping to protect nitrogen leaching in many of our crops. And I think that in many of our crops where we put a lot of fertilizer up front at planting time, that early in the season when the root systems are small, that's the time in which the crop or the nitrogen is most vulnerable to leaching. So I think if we can fix some of this risk early in the season by using some of these controlled release materials, I think it'll be a step in the right direction. So in our programs, we're especially interested in how we can utilize these materials early in the season before the root systems really get established. It certainly is showing that it can offer a lot of flexibility in our programs. And over the past 3 years where this intensive work has been done here, there's a number of different crops that have been worked on. In the case of watermelons, I've been doing the field work on it, and Kevin Athern has been helping on the economics of it. In the case of carrots, myself and Charles Barrett, Michael Dukes, and again, Kevin working on the economics have been important to this. In the case of corn, Dee Broughton has led a lot of the trial work that's been done in this area, along with Dr. Dukes as well. And Jay Capasso is going to describe to you some of the work that he's been doing in Columbia County, working directly with farmers. So I'm not going to steal a lot of Jay's thunder on the corn part of it. So those are the three main crops that we've been working with over the past few years. This year, we've initiated some work on 2 new crops. One would be potato, and Sylvia Willis here in Suwannee County is leading that effort. And also we're starting to work on snap beans, and Prissy Fletcher and Christian Christensen over in the Hastings area started this work in the fall. And then this spring, we are continuing that work here in the Suwannee Valley. So those are the 5 main crops in which we're working with this. In the case of corn, just a little bit of information here that we're going to focus today's efforts on controlled release fertilizer, and we have a number of large on-farm trials here. So corn is one of the crops in which we feel like that's our best opportunity to reduce the nitrogen loading in this BMAP area. And there really are 2 options that the farmers have. One would be to adopt controlled release fertilizer programs, and the other one would be to implement equipment that would better suit side dressing of conventional materials or even controlled release materials. So I'm not going to say a whole lot about corn. I'm going to leave the rest of that story to Jay. This year, when we implemented the snap bean work, we've got, in all of these cases, I feel like we've really tried hard to incorporate farm cooperators in our programs. And so in this case, 83 Farms is a local snap bean producer that's helped guide us in terms of the treatments and the rates and things like that. And we've implemented these two trials here just in the last month at the center. One of the companies is Purcell that makes controlled release fertilizer, and the other one is Harrell's. Those are the two different companies or the manufacturers where we're evaluating their program. And a lot of this research, we're looking at just the controlled release nitrogen portion of this crop. So the rest of the fertilizer, we want to try to make sure that it's adequate across the board, and then try to focus in on the controlled release nitrogen part of these particular trials. So we've got basically five different rates of controlled release nitrogen and 5 different rates of conventional nitrogen with different methods of application, some of it banded and some broadcast. So it'd be interesting to see what happens here. This is one of those crops that's a relatively short season. It is being done commercially in parts of the state. And so we're going to take a look at it up here on our deep sands. This year also a new crop project was initiated by Sylvia Willis. She was able to attain some funding support through the FDACS and IFAS BMP mini grant program. And Black Gold is one of the large potato growers up in this region. And so the combination of support and guidance from Black Gold, Harrell's would be the company that's supplying the fertilizer for this trial. And I don't want to leave out Waters Ag Labs, that they have been a partner in this and sort of an in-kind thing, giving us a really reasonable rate on a lot of our soil and tissue testing that we conduct in these trials over the course of the season. Some of you might see this picture and say, that can't be potatoes, they're not on a bed. This particular company here has adopted through time a little different cultural practice that is actually on the flat. And that width of that area, I think it's about 11 feet wide when they go in and plant, but they're not on a raised bed. And actually that helps us in this deep sandy soil area here to get better utilization of irrigation. So if you have a high raised bed, it's hard to get the moisture into the center of that bed, whereas on these flat production systems, they've been able to do a lot better job of irrigation. And I think that they've indicated somewhere between 15 and 30% reduction in water and a lot better utilization of the nitrogen in particular by going to this system. So that conversion this year was essentially 100% of their acreage in the Suwannee Valley area. The other large farm operation that's growing potatoes here would have the traditional method of the raised beds that would be so typical of growing potatoes. So there's a combination here of both conventional and controlled release as well, and a pretty wide range of rates for the nitrogen component of that as well. I want to move into sort of one of the crops that I've been spending a good bit of time on in the last few years, and that's going to be watermelon. We started this work back in 2019. Also was able to utilize BMP mini grants to help get some of this work started. And here we've been able to compare conventional fertigation programs to a controlled release program where we put all of the fertilizer under the bed up front in the case of the controlled release. In the case of conventional, we only put a portion of the fertilizer under the bed, or the fertilizer nitrogen under the bed, and the remainder would be fertigated over the course of the season. And we had really good results in the controlled release. If you take the picture on the right-hand side and look at that, it's really hard to pick out where the treatments are and where one treatment starts and where the other one stops. And that's kind of what the results typically have shown, that we've been able to do a really good job with watermelons. And if you look over on the right-hand side of the screen is mostly what I want you to focus on. And that is that we basically had 4 treatments. We had soluble nitrogen and controlled release nitrogen, utilizing the BMP irrigation rate. And in that situation, we were able to show higher yields where we did a better job of managing the irrigation. The 2 right-hand bars, the yellow and the blue, are reduced there, and that's where we forced a higher irrigation rate than what we would normally use, and we just went with 1.5 times the irrigation rate. So we know that we are losing effectiveness of the nitrogen when we over irrigate. So that gave us an opportunity to, over those 2 years, to gain confidence, to be able to try to take this onto some large on-farm scale demonstrations. And this is where we really get into the opportunities for the fine tuning. There's only so much fine tuning that you can do in small plots on a research center. And then the real world out on the farm is where there's opportunities to learn an awful lot of challenges that we never thought of in our small plots, and come up to the reality of fine tuning these programs when we go into the farms. So going into this year, we had an opportunity to do some of this work through the BMP mini grant program. And also there was some pieces of the puzzle that we felt like we really needed some help with, primarily labor. And so we have a good interaction with the Florida Watermelon Association, and we went to them to see if they would help us to partner on the funding side, which they did. So there are 3 different farm locations here, one in Lafayette County, one in Gilchrist County, and one in Levy County. And the material that we're using here is Harrell's fertilizer. And the reason that we're using Harrell's is that's where we had the research before we went on to the farm. So I think that we would equally enjoy the opportunity to work with other manufacturers. But before I'm comfortable to go on to a farm, I want to know that we've got some confidence based on previous research. And so Harrell's is the only one that we had that with. So there's no bias here necessarily. It's just that that's the company that we had the confidence in the previous research. So the extension agents that are involved here: Mark Warren in Levy County, Tyler Pittman in Gilchrist, Tatiana Sanchez in Alachua, myself and Kevin Athern up here, and I manage the one in Levy County in the absence of an ag agent at this point in time. So we were able to apply the material, and Harrell's has a fertilizer distributor that helps in the application methodology. And Jay Skillman is the contact person with Harrell's and has been a tremendous resource for us in putting these projects together. So we calibrate the spreader, we base it on linear bedfoot methods, and that was the first fine tuning that we realized the day that we went out to do this. And talking with the farmer, it was obvious that we needed to sort of have a sort of step back and go through the math exercise of calculating how much fertilizer should be put on in a linear bedfoot method. And so we've been able to do that, and we feel like there's an opportunity there. When you get row spacing that are wider than normal, there probably is an opportunity to change the fertilizer dynamics underneath that bed. So I'm going to leave that for another day, but linear bedfoot method became a really important fine tuning for us here in this process. So we did the calibration of each of the rates. We applied it, in this case, the slide in the middle to the sort of the center of the bed, and maybe an 8 to 12 inch band that came out of the back of that spreader. And then each farm handled it the way that they would normally handle it. In this case, rototilled that fertilizer in more uniformly, and then raised the beds and covered it with plastic mulch and drip irrigation. As many of you know, that there's a need for water quality data to go along with these kinds of projects, and lysimeters are really difficult to implement on farms for many reasons. And so we've depended on 2 methods here. In the far left, we are using a manual auger and taking soil samples from 0 to 6, 6 to 12, and 12 to 20, or 0 to 12, 0 to 12, 12 to 24, and 24 to 36. And each of those are put into separate bags and sent off, and we measure the nitrogen in each of those soil samples. So that's one method that we can sort of track where the nitrogen is in that crop profile. And we certainly could make the assumption that once it gets down below 3 feet in the case of watermelons, that nitrogen is probably no longer available to the plant and it's not coming back up. So we got a measure there that we can help on the water quality impacts. The other one, the soil moisture sensors, give us an opportunity to also track the overall salinity. And so we're tracking the movement of nitrate and other fertilizers in this particular case. So those are the methods that we're using on farm that are at a reasonable expense to us in these mini grants. So in the case of watermelons, we even though I sort of thought I knew what was going on working with watermelons for the number of years that I have, I'm not sure that I have ever paid that much attention to early in the season, even before planting, in terms of what's going on with the fertilizer. So we learned that the conventional fertilizer, even if it's underneath the bed, still has a couple of points of vulnerability. One is you can still get some leaching and really, really heavy at rain events. And the necessity to keep those beds moist forces the farmer to at least periodically use drip irrigation to keep the beds moist. And there's the second point where leaching could potentially be a problem. So early in the season is clearly the area where we have the greatest risk of both nitrogen and potassium leaching, but we're in this area mostly concerned about nitrogen. So we learned that under the controlled release fertilizer in those same circumstances that we're not losing nearly as much of the fertilizer. In fact, the part that's still in the granule is protected. The only part that is vulnerable to leaching there would be the part that would have been released up to that point in time. So we feel as though that's going to really, really help us in the case of the watermelon crops. And I'm not sure that we need to depend entirely on controlled release fertilizer for the entire season, but it does suggest to the growers that they would prefer to put it all underneath the bed so they don't have the expense and the labor involved with fertigations over the course of the season. So obviously cost is a big factor here, and Kevin is helping us to try to figure out what's going to happen there. So what we have seen so far, I'm really encouraged that these controlled release materials could play a role for us. And however, it may take some type of an incentive program to help the growers to adopt this because it is going to be more expensive. And it's really the cost sharing on the polymer coating part of it, not the fertilizer itself, but the technology that I think would be fair to suggest some of that. In the case of carrots, we have sort of a similar progression where we were looking at small plot trials here at the center and are working towards getting on farm. And but I would say that we're probably a year behind where we were in the case of watermelon. So we've not gone on farm with this yet. We take a lot of data, including the quality parameters of these carrots. This was our pandemic method where we didn't have any labor, but I could set my iPhone up on top of the top table, take a picture of what that image would be like on the right-hand side, and then later go back and take those measurements at a computer screen. So that was one of our ways to get this data and not lose it, even though we had very few folks here available to us. So in a similar situation to what I showed in the case of watermelons, you can see that the blue and the orange bars on the center and the right of the screen are in some cases just as good, but overall, we're not quite able to do exactly what we are able to do in the case of conventional fertilizers. So we got a little bit more fine tuning to do in the case of controlled release materials. So over the years of working with small plots, I felt like, okay, I want to take a step away from the small plot work and give an opportunity to the three manufacturers, in this case, Floracan, Harrell's, and Purcell, to sort of give us your best shot of a controlled release material that's going to have 150 that we would be able to apply a rate of 175 or 200 pounds of nitrogen to the top of the bed, and that's what you kind of see here on the left and the right, the various controlled release fertilizer materials. carrots presents a really challenging crop curve, and it's almost like a roller coaster ride over the course of the season, where it's a very long season and we have periods of hot and cold, which makes the polymer timing really, really difficult for carrots. And it's my opinion, based on what we're seeing, the observation is we probably should not be trying to depend on one application up front to do it all. So could we put maybe 75 or 80% of the fertilizer in a controlled release form up front, but hold 20% in our holster and utilize that through conventional applications when we really know that we need it, either during or after a cold period or after a heavy leaching rain event, leave that other material available to us. And that's what I think that this trial, although we haven't harvested it yet, that's what I think we're going to learn from this. We've also looked at some fine-tuning methods in terms of the different ways that we place the fertilizer on top of the bed, and then just press it in on top of the bed, lightly incorporate it, fertilize it on the flat, and then build the bed over top of it. So we've got on this trial several different ways that we are putting all of that together. So the fine tuning part for carrots would be that it looks like we can get equal to, at least similar yields to our conventional programs, which require either several passes of equipment or several fertigation events through the pivot. And to me, it looks like it's going to be a lot easier to meet the IFAS rate requirements through some of this material being through controlled release fertilizer. So during cold periods and leaching rain event periods, that's when I think that it would be wise on our part to have the ability to have some nitrogen still left before we get to the IFAS rate to be able to use it in a timely manner. So I do believe that this leaching rain event clause will be helpful to us as we develop a full BMP for carrots. So it might be that the best strategy is to put part of it, most of it up front, and then the remainder of the season based on strategy through leaf analysis or leaching rain events to figure out that part of it. But it certainly is a 4Rs story as far as I'm concerned. Looking at different placement, rates, timing, all of that has been critical for what we're doing here. But I am really encouraged about the way that this is coming together this year. And my hope would be that next year we would be ready to take this onto a farm and look at some large scale demonstrations like we're doing with watermelons. So with that, I'm going to turn it over to Jay Capasso, and Jay is going to talk about the work that he's been doing with controlled release fertilizers on field corn and some of his on-farm trials in Columbia County.
Thank you, Bob. So I'm going to be talking a little bit about the control release fertilizer trials we've done in Columbia County for the past few years now. So for last 3 years, since 2019, we've been doing trials comparing banding or side dressing control release fertilizer to grower standard practices, which generally include broadcasting conventional fertilizer. These trials have been funded through BMP mini grants in the 2019 season and the 2021 season. And during the 2020 season, we didn't have access to the BMP mini grant. So we had a Stetson Sustainable Farming Fund grant that we were able to access. And we've worked with about 4 different producers now on these projects. 2 producers were in Columbia County. And most of this presentation today, I'm going to be speaking about results I've seen working with one of the producers for the last 3 years since 2019. In 2020, we also had a producer in Suwannee County. And in 2021, we have a second producer in Columbia County and a producer over in St. Johns County. So for the Suwannee County producer, we were working with Extension Agent Sylvia Willis, and the St. Johns County agent, Chrissy Fletcher, for the St. Johns Cooperator. So the goals of the on-farm trial were to promote BMP practices, so side dressing or banding, which is an efficient fertilizer application method. You can see that in the first picture here. You see a side dressing rig going through young rows of plants and applying fertilizer efficiently in a straight line to either side of it. And that's compared to broadcasting when you go throughout a field and you uniformly apply fertilizer. We also promoted the use of soil moisture sensors, and in some cases, the soil moisture sensors were written into the grant, and in other cases, we were able to access loaner probes through Charles Barrett here at the North Florida Research Education Center, Swanee Valley. Another goal of the on-farm trials were to compare yield, nutrient tissue sample analysis, and soil nitrate data at various depths between the control release fertilizer treatment and the grower standard practice. So I'm going to talk about some of the pros and cons of banding control release fertilizer. So one of the pros is that banding is a more efficient fertilizer application method than broadcasting. As I was just describing, it is said when you ban fertilizer or side dress fertilizer in corn, you can apply about 30% less fertilizer. Control release fertilizer can be applied in a single application along with the starter at the beginning of the season. So I think that's a huge pro in terms of, for my farmers and their time. I'd say the average age of my farmers in Columbia County is probably somewhere around 70 years old. So if you're able to cut back on the amount of labor they have to do, I think many would be very willing to adopt the practice. And so the control release fertilizer can go out at planting, just before, just after. And generally there's a liquid starter application of something like a 28005, maybe 30 or 40 pounds of nitrogen is in that gets applied. So it goes along with the starter application. There's a higher cost of control release fertilizer, which is a negative in terms of the farmer's point of view, but potentially from an environmental point of view, the higher cost of control release fertilizer could incentivize more efficient fertilizer application practices, such as banding or side dressing. Another pro is that it's beneficial for growers who are unable to fertigate through center pivot irrigation. Here in Swanee County, I've noticed that a lot of producers fertigate through their center pivots, but over in Columbia County, I have at least one producer, the producer most of the data from this presentation will be from, who's under hard hose irrigation, which is basically like a big sprinkler. And then I have a couple of producers that have expressed to me that they don't want to fertigate through their center pivots, even though they have access to a center pivot, because they're worried about the nitrogen fertilizer degrading their center pivot over time. A con would be that it takes longer to side dress or ban fertilizer generally compared to broadcasting. Broadcasting is a quick and efficient fertilizer application method. There's also fertilizer applicator capacity issues for large acreages, especially with side dressing rigs. These side dressing rigs were created to be able to do split applications of conventional fertilizer. And it's difficult when we're trying to apply all the fertilizer at once, minus that liquid starter at planting, to be able to have enough capacity without having to refill the side dressing rig over and over again. So I'll be talking about that a little bit in the next slide. And then another con is the higher cost of control release fertilizer, which is the main barrier to why many producers haven't adopted the practice. And you see the picture here in the right-hand corner. This is from my first season doing the on-farm trial in 2019. You can see there was broadcasted corn. This is towards the beginning of the season, and side dress corn with the control release fertilizer. And in this picture, you can see that the side dress control release fertilizer corn was noticeably ahead at this point in the season. I think the broadcast conventional corn caught up a little bit towards the end of the season, but towards the beginning of the season, you could see where in the field the side dress control release fertilizer treatment was. So I'm going to go over some of these fertilizer applicator rigs now. This is a typical broadcasting rig in the left-hand corner here. So it uniformly spreads fertilizer throughout the field. And again, a very fast and easy way to apply fertilizer. And you can tell in the hopper there, in this case, we're applying control release fertilizer because the grower wanted to compare broadcasting control release fertilizer to banding control release fertilizer to their standard grower standard practices. And you can see that you can carry a good amount of fertilizer in there. I'm not sure the exact capacity of this particular broadcasting rig. It's one of my growers, but you can carry a good amount of fertilizer. And then you have the side dressing rig. This is a 4-row first product side dressing rig. And in each of the hoppers there, you can see 2 of them, you can carry about 1,200 pounds of fertilizer. Or so in a total carrying capacity, you're probably somewhere around 1.2 tons of fertilizer. So this is a 4-row applicator, and this is a good machine or a good applicator for a grower who maybe has less than 200 acres of corn, I would say. And, even if they're somewhere around 200 acres of corn, they might want to push up to a 6-row applicator because carrying capacity can be an issue. And then in the right-hand corner, you have the Harrell's banding applicator. This is a 8-row applicator, and it can carry about 5.5 tons of fertilizer. So they created this machine, I believe this past year or the year before, because they were running into these issues with fertilizer capacity. And it can efficiently, it just drops fertilizer on top of the row. And generally the practice is to come back and use strip tillage or to plant on top of the band of fertilizer to be able to incorporate it a little bit into the corn row. The difference between the side dressing rig and the banding is that the side dressing rig is going to get fertilizer into the ground at a certain depth, maybe around 3 inches or so. And the banding is just dropping it on top of the row, and you could leave it there or you could find a practice to incorporate it. So fertilizer placement can be tricky. That's one issue we've run into with these trials. And these pictures are from a couple of weeks ago from a Columbia County cooperator who's growing silage corn on twin rows. And you can see that we use the Harrell's banding applicator in this trial, and it dropped fertilizer in the left-hand picture, basically perfectly right on top or right between the 2 twin rows. You can see a mound here on the left, a mound over here, and it was between the two. So that was perfect placement. However, much of the field didn't end up looking like that. We went through the field and we banded the fertilizer using the Harrell's applicator, and then we had the farmer go back and plant on top of the bands of fertilizer. But for the most part, he was off a little bit. It was over in the left, basically on the left-hand side of one of the twin rows of corn. So we'll see how it does. This is the field where we're comparing banding control release fertilizer to broadcasting along with the grower standard practice. So we'll see how we're able to perform even though we have this fertilizer placement issue. This is an example of side dressing control release fertilizer. You can see you have it in the soil about maybe 3 inches or so. And in this trial, we're actually going to be comparing this year side dressing control release fertilizer to side dressing conventional fertilizer, because one of my cooperators went ahead and got a side dressing rig through the Suwannee River Water Management District using cost share. So, this is great to get the control release fertilizer in the ground, but he started asking me questions because we're going to go back in his grower standard practice and apply conventional fertilizer at 30 days after planting and 40 days after planting. And he was worried about running over the crop roots at that point. So we're going to be working with adjusting the depth of the side dressing rig during the 30-day application, maybe lighten it up a little bit. And then maybe in the 40-day application, we'll take those discs off and just drop it on top of the row. So I'm going to quickly go over these next 2 slides. Basically, all this data is from the grower cooperator I've worked with since 2019. And during the 2019 season, we side dressed control release fertilizer. We had 6 different treatments, and then we broadcasted conventional fertilizer and had 6 different replicates of that. And you can see we had a 20 bushel per acre increase in yield on average in the banded or the side dress control release fertilizer compared to the broadcasted conventional fertilizer. In the 2020 season, we banded the control release fertilizer instead of side dressing. This was back in March when the world shut down last year, and we had 4 different replicates of each. And these are the average yields that we found between the 2 treatments. This is the soil nitrate data. So we collected soils from 0 through 6 inches, 6 through 12 inches, 12 through 24 inches, and 24 through 36 inches from the broadcasted conventional fertilizer treatment and the banded control release fertilizer treatment in 2020. And we basically just found a more gradual release of fertilizer or nitrogen in the banded control release fertilizer treatment. So in conclusion, we found slightly higher yields in corn fertilized using banded control release fertilizer compared to broadcasted conventional fertilizer. Soil nitrate data indicates a more gradual release of nitrogen in the banded control release fertilizer treatment compared to the broadcasted conventional fertilizer treatment. These on-farm trials have provided opportunities to educate local producers on BMP practices, and this has led to the adoption of agricultural cost share through the Suwannee River Water Management District on soil moisture sensors and a side dressing rig. And we also, at the end of last year, we got the Stetson Sustainable Farming Fund grant. And at the end of the season, they opened up proposals again because they had money left over. And I helped the producer apply for a grant for a Great Plains no-till drill. And he was able to receive the equipment. It also has the capacity, basically it's going to help him plant cover crops without disturbing the soil. And it has the capacity to efficiently apply fertilizer by the row. And with that, I'll wrap it up.
Thank you, Jay. Thank you, Bob, for your great presentation. So Jay, I have a question for you. Was the farmer that was planting the twin row silage corn planting with an RTK, same question for the Harold's band fertilizer drop application?
So
Yeah.
we used the Harrell's banding applicator, and it basically, we dropped it. And then after that, the farmer went through and planted on top of where the fertilizer was banded using the Harrell's applicator.
Okay, thank you. The next question is, so what was the name of the grant that Robert just mentioned, the no-till drill cost share? I'm not sure about that. Is that Bob?
Computer and it shows Robert.
Okay. So I believe that grant was probably a BMP mini grant.
Mhm. I believe so. Okay, very good. Mark, are you there? We have plenty of questions for you. And audience, we have a quick survey for you to fill. It's less than 1 minute. Please fill that survey. Emily, if you can provide the link for the survey in the chat box, that'll be great. This survey usually takes less than 45 seconds for you to fill. But that will help us to improve the BMP Summit for the next year and also help the presenters to improve their presentation and the information they are covering. Please click on this link for your to fill up the survey. In the meantime, Emily, if you can also provide the QR code for the CCA credits, that'll be great. Bob, can you stop sharing? So I think Emily can share the screen and provide the QR code. Here we go. Mark, we have some questions for you. Oh, here is a QR code. All right. So the question for you, the next question after we left, the next session, the next half of your session. Goodness, where we were. Okay, so I understand that Everglades growing area is actually moving phosphorus. Water coming into the EAA from lake has higher P than the discharge water. Is that true?
Yes, it is. And hello, Charles. Yeah, it has to do in part with the elevated levels in Okeechobee that kind of came up because of some high water events. But in general, the EAA is receiving waters that might be on the average of 120 micrograms per liter of phosphorus, and it gets discharged from the EAA around 90. Now that's going to vary year to year. Those are some numbers that I've heard kind of as averages. So yes, the EAA is assisting in the removal of phosphorus as water moves south. That water, however, even at 90 micrograms per liter or 90 parts per billion, would be 9 times higher than what is acceptable discharge into the Everglades protection area. So that water still has to go through the stormwater treatment areas. And so it's correct. And this gets back to the idea, yes, some of that phosphorus may be supplementing. I don't really know about the pea fertilizer applications in the EAA, but that could be supplementing some of those applications, which would be a benefit. However, we could also look at it in this kind of equilibrium where that load of phosphorus that got transferred to the lake is now being transferred to the EAA. And so that phosphorus, if not taken up by the biomass of whatever crop is there, is now going to accumulate in those soils. And so that can be a legacy load that's now developing in the EAA. But the answer to the straight question is yes, the inputs from Lake Okeechobee are higher in concentration than the outputs from the EAA.
Thank you, Mark. Next question is.
Hey, Lakesh, excuse me, just 1 second. If we could go back to the question, I think that we have a better understanding now, the question on the cost share for the no-till drill.
Yes.
That the project itself that Jay was doing was a BMP mini grant, but the cost share for that was through the Stetson Sustainable Ag Grant. That's where the equipment would have come from. So that there were two different sources of funding that he was using in that grant, but the equipment itself, if that was the question, where the no-till drill cost share came from, it was through Stetson.
Thank you, Bob. Thank you for clarification.
You're
That's
welcome.
great. All right, Mark, we have your next question. South Florida Water Management District recently announced they will use ALM applications to remove phosphorus from C42 reservoir. Commence.
I guess I don't know about that explicitly. Alum is a very effective tool at removing phosphorus. It's a form of aluminum that's highly reactive with phosphorus. You know, one of the big challenges is, of course, settling it out. So it's goes in as a liquid. It forms a precipitate that alum with phosphorus now settles to the bottom as long as the conditions are calm enough. But then, of course, now you have to deal with this particulate matter and do something with it. And so, I mean, it's a very effective tool. You know, it's used as a clarifier in a lot of water treatment plants. And so you have a water treatment residual that oftentimes has excess aluminum that can still bind phosphorus, and that's used in certain applications. So, I mean, that unfortunately what sometimes happens to try to address the issue is literally a chemical reactor that has to mitigate for the amount of phosphorus loads that are otherwise impacting ecological systems. So, I mean, I would prefer to see treatment wetlands out there, but the area involved to have the same phosphorus removal much larger than the footprint of a chemical treatment plant. So. But yeah, sometimes that's what has to happen to remove the loads.
Thank you, Mark. Bob, hang on. We have a question for you after this question for Mark. Mark, the next question is a little longer. Let me read it. South Florida soils are higher in calcium and have a higher pH around 7.4 plus. Why isn't calcium P and magnesium P used in the SPSC index? Why is only iron and aluminum used? Also, we have found that our soils can hold much higher amounts of phosphorus because of calcium levels. What work is currently being done on calcium P in Florida soils? Also, how accurate is Mehlich 3 in determining phosphorus levels in soils with higher pHs?
Yeah, no, so that SPSC index is really was developed for acidic soils. That's the majority of the Southeast is more of the acidic condition. You're absolutely right. You get down to South Florida, you have higher pH where you start interacting with the underlying lime rock, limestone, and under those conditions, calcium would be the driver for phosphorus retention. And the SPSC is not applicable to those conditions. I would have to ask Vemela and Nair to see whether or not that's being adopted or adapted to those situations. I can't speak very well to what research is going on with Mehlich 3 and the specific calcium-bound phosphorus. I know that there are other extractable soil extraction methods that are better under those calcium levels. I don't know, Lakesh or Bob, if you want to jump in on that, but the other one would be Dr. Malavarapu Rao, who runs the soil testing lab. But there's a lot of work going on in those areas. I just am not aware of the specifics of that research.
I can give some update on that. Mehlich 3 may not be the test across all South Florida. There is some research going on to recalibrate Malik-3 and also to determine if Malik-3 is the test for South Florida. It's not a universal across Florida to adopt one test. So there is some people that are working with Dr. Kelly Morgan from Immokalee, center director in tomatoes to recalibrate the phosphorus test in tomatoes, possibly next few years. Bobby, do you have something to say on it?
I'm just going to say that that's also the spirit, isn't it, Lakesh, of the upcoming 2 or 3 year project that Dr. Angle wants to implement on both corn and potatoes at different locations in the state to try to take a closer look at phosphorus. So yeah, that I think, Mark, that funding will at the earliest start this coming fall. So it's in the works now, but probably the fall season for getting ready for potatoes will be the first opportunity to actually implement that research. But it'll be across the state at several different locations and a high priority for Dr. Angle.
Yep, that's true. Thank you, Bob, for this update. Okay. We have a question for you, Bob. What are the advantages of advanced fertilizer? Does advanced refer to efficiency or an environmental impact?
Yeah, I think there's probably a little bit of both of that in the efficiency piece. I do think that mostly what we're targeting is trying to increase or improve the nitrogen use efficiency. In the case of nitrogen fertilizer, we're trying to improve that efficiency at the crop level. And then what I believe will happen is that the environmental impacts are going to be a result of that improved nitrogen use efficiency. So I think that these advanced technologies that we're using in polymer coated fertilizers capture both of those. Actually, it probably refers more to the improvement in the efficiency of nitrogen uptake, but I think the result of that is clearly going to be an opportunity to improve the environmental benefits.
Thank you. Mark, this is another question. I think it's a follow-up. After doing a quick search of South Florida Water Management District website for the reference to 80%, I'm wondering if you can clarify for the audience if your statement was regarding more than 80% of the net phosphorus imported into the northern watershed, excluding Upper Kissimmee and Lake Apopka? No, it's Apopka Basin, stored in soils and sediments referenced at this path. I think there's a link to that. Or if you were referencing a different source that estimate that 80% of the necessary load reduction from the northern sub-watersheds is associated with the legacy P. Thanks in advance for the important clarification.
Yeah, no, I appreciate that, Sarah, for bringing that up. I would have to go back and look at the document I did. I haven't opened it up, but that may very well be a correction, an accurate correction, that the 80% was in relation to the historical load being assimilated into the soils of the basin. That said, I will need to go back and determine what, and I don't believe they can actually determine what exactly that fraction of load from legacy is in the basin, but my understanding is the majority of it is being driven by the legacy load in the basin, because new inputs are, I mean, there's no biosolids application allowed anymore in there. There's a lot more scrutiny over any sort of inputs of P fertilizer. So the actual 80% number, I believe you may be correct, was a misstated relative to that document, but I'll have to look at the document again, but that's a good point of clarification.
Thank you, Mark. We do not have any more questions. Audience, if you have any question, you can reach out to the presenters directly, or you can send me an email and I can convey your question to the presenters for the answer. Again, we have CCA credits, and the sheet, sign-in sheet is attached. There is a QR code in that for your reference, and there's a quick survey that we want you to reply to that. It's less than a minute that you can reply using the survey link. That will help us improving our extension program for the next year. With that, I would say thank you everybody for your presentations. Mark, Bob, and Jay, thank you for being present today and this excellent information. Thank you, both of you, for answering all the questions. If anybody has any question, please let me know or type in the link or send me an email. Thank you, Emily, for helping in organizing this BMP summit and session. And thank you, Dr. Dukes, for your help in developing this beautiful program, for a very informational program for us. Thank you. With that, the meeting is adjourned.
Thank you, Lakesh. Appreciate it.
Thanks, Lakesh. Thanks for the opportunity.
Thank you.